We're looking at section 7.2 today. This is about hypothesis testing for the mean when sigma is known. So in section 7.1, we figured out what a hypothesis test was. Now we want to see how it actually works. So we have some definitions from 7.1 that we want to review again. The first is the level of significance, alpha. And so that's the maximum allowable probability of making a type 1 error. And then the p-value of a hypothesis test is the probability of obtaining a sample statistic with a value at least as extreme as that obtained from the sample data. One more little thing here. We use the p-value decision rule to make our decisions. And how does that work? Well, if p is less than or equal to alpha, we're going to reject h0. And if p is greater than alpha, we fail to reject h0. So those are the things that we need to recall from section 7.1. So here's an example. The p-value in a hypothesis test is p equals 0.0322. We want to figure out our decision for a couple different situations. What would our decision be if alpha was 0.05? And then what would the decision be if alpha was 0.01? So let's start with the first one. If p is 0.0322 and alpha is 0.05, we're going to compare these. That's what the p-value decision rule is. It's a comparison test. So which one's bigger, which one's smaller? And clearly the 0.0322 is smaller than 0.05. You'll notice I put 2 zeros at the end of the 0.05. That way the decimals have the same length, and it's easier to tell which one's bigger. So p is less than alpha. And if p is less than alpha, we reject h0. For part B, we still start off with the same p-value, but now we're comparing it to alpha equals 0.01. And again, I'm putting 2 zeros at the end to make the decimals the same length. Now the 0.0322 is greater than the 0.0100. So p is greater than alpha. If p is greater than alpha, then we fail to reject h0. So that's how we use that p-value decision rule. This is basically how the end of the problem would look. We go through a process to figure out the p-value, and then this would be how we use the p-value decision rule at the end of that process. So we have a note. The lower the p-value is, the more evidence you have to reject h0. Notice when we looked at the inequalities at the end in the p-value decision rule, we had the situation where p was 0.0322, and we rejected h0 when alpha was 0.05, but we failed to reject when it was 0.01. If p had been smaller, it would have been possible to reject in both situations, if it had been less than the 0.01. So you can see that shrinking the p-value will give you a greater opportunity to reject h0. Let's go ahead and go back. All right, so once you've got the p-value, that's how you make the decision. But what's the real question? The real question is, how do we find the p-value in the first place? Where does that number come from that we use to make our decision in the p-value decision rule? So let's talk about finding p-values. So this process depends on what type of test we're performing. For a left-tailed test, which means that the alternative hypothesis has a less than symbol, then p is going to be the area in the left tail of our distribution. If we're looking at a right-tailed test, which means that HA contains the greater than symbol, we're looking for the area in the right tail, so the distribution would look like this. And then for a two-tailed test, HA contains the not equal to sign, we're looking for twice the area in the left tail. Why not just say we're looking for the area in both tails? And the answer is we are doing that. We are looking for the area in both tails. But because of symmetry, all we have to do is find the area in one tail and double it. And why do we choose the left tail? Well, remember that the standard normal distribution always has areas to the left. So the left tail area is a little bit simpler to find than the right tail area. But if you wanted to find that area in the right tail and double it, you totally could. It would just require a little extra work as you go through it. Okay, so let's look at an example. If you are performing a left-tailed test and your test statistic is z equals negative 2.18, find the p-value. Then decide whether or not to reject h naught given a level of significance alpha of 0.02. What are we going to do here first? We know it's a left-tailed test and that this test statistic is z equals negative 2.18. A sketch of that distribution might help us understand things more clearly. So now what? What are we going to do? Well, we need to look at the standard normal distribution table. So here's the negative side of the standard normal distribution table. We'll look up the negative 2.18. And for negative 2.18, we see the 0.0146. Let's get rid of that. When z is negative 2.18, then that means the area is 0.0146. That's our p-value. That's the area in the left tail. So now let's perform the p-value decision rule. Let's get rid of that, slide this up a little bit. So we're going to take our p, which is 0.0146, and our alpha, which is 0.020, and compare them. So in this case, the p is less than the alpha. If p is less than alpha, we reject h naught. So our decision here is to reject h naught. How about a two-tailed test? What would that look like? So here's an example. If you're performing a two-tailed test and your test statistic is z equals 2.09, find the p-value. Then decide whether or not to reject h naught given alpha equals 0.03. All right. So a sketch of the distribution might help. We want a two-tailed test. So we've got two tails shaded, one to the left of negative 2.09, the other one to the right of 2.09. So remember what we said. We're just going to find the area in the left tail and double it. So to find the p-value, determine the area to the left of negative 2.09 and double it. How do we find that area? We need the standard normal distribution table. So let's look at the negative side because that z on the left was negative 2.09. So here's the negative side of the standard normal distribution table. We look for negative 2.09, and the table value there is 0.0183. We need to use that to help us find our p-value. So let's go back. So if z is negative 2.09, then the table value was 0.0183. But that's not the p-value. Remember, the p-value is twice that amount. So p is equal to 2 times 0.0183, which is 0.0366. So now we can go ahead and perform our decision rule. We take our value of p, which is 0.0366. We compare it to our value of alpha, which is 0.0300, and we find out that p is greater than alpha. And if p is greater than alpha, then our decision is to fail to reject h naught. So in this particular case, we would fail to reject h naught. Now, a very common mistake that's made on these two-tailed tests is they find the area to the left of the z-score, the 0.0183, and they forget to double it. And if you look at this problem, if you had used the 0.0183 instead of the 0.0300, then you would have seen that 0.0183 is less than 0.0300, and you would have rejected h naught. So using the wrong area would have led you to the completely wrong choice for your decision at the end. So you have to be very careful in these two-tailed tests that you don't forget the step where you double the area in the tail. Okay. So how does this z-test for the mean actually work? You're always going to use this when the sample is random, sigma is known, and you have a population that's normal, or the sample size is greater than or equal to 30. So we're going to use stuff from the sampling distribution of sample means to help us, which means that the z-score is found by doing x bar minus mu over sigma of x bar. And remember, sigma of x bar can also be written as sigma over the square root of n. So what's our process? First thing we're going to do is verify that the sample is random, sigma is known, and the population is normal, or n is greater than or equal to 30. Next, we're going to state our hypotheses, H0 and HA. What's our level of significance? Sometimes, most of the time, that's going to be given to you. But sometimes if you're developing your own statistical study, then you're free to choose whatever level of significance you want. How much probability of making a type 1 error do you want to allow within your investigation? Most of the time that's set at 0.01 or 0.05, but you can set it at 0.03 or 0.02 or something to your liking. You want to be aware of the fact that this is an area where bias can creep into your problem. If you do the entire hypothesis test and then determine what your alpha is, then you may be figuring out your alpha so that you get one result or the other. You may want to reject H0, so you pick the right kind of alpha to reject H0, or you may want to fail to reject H0, so you pick an alpha that's of sufficient size to fail to reject. Because the smaller the p-value is, the more evidence you have to reject the null hypothesis. So for whatever p-value you find, if you make the alpha value larger, then you're going to automatically reject. And then if you make it smaller than the p-value, then you're going to automatically fail to reject. So you want to specify your level of significance at the beginning before you've done any calculations to avoid any potential biases creeping in. Then you find your test statistic z. That comes from interpreting the problem itself and using the available values to construct your z-scores. Then what's your test type, right? Remember, the test type is determined by HA. Is it a left-tailed test where HA has a less than symbol, a right-tailed test where HA has a greater than symbol, or a two-tailed test where HA has the not equal to symbol? Then you find your p-value. That's using that z-score on the standard normal table to find the area in one of the tails, or finding the area in the left tail and doubling it. Then you're going to compare the p to the alpha to make your decision using the p-value decision rule, and then of course interpret your results at the end. So let's see how that would work in a full-blown example. The Neighborhood Watch on Leisure Avenue claims that the mean speed of cars traveling on Leisure Avenue is greater than the speed limit of 35 miles per hour. A random sample of 100 automobiles has an average speed of 36 miles per hour. The population standard deviation is known to be sigma equals 4 miles per hour. Is there enough evidence to support the claim at alpha equals 0.05? Now you may wonder, why would anybody ever do this? This doesn't make any sense to me at all. This just seems like a random made-up problem. And it's absolutely not. So, have you ever been driving and there's a little box on the side of the road and there's 1 or 2 black cords that stretch out across the road, and you drive over them and you don't think anything of it? You're like, what is this? So what that is it's a traffic flow device. And the number of cords determine its purpose. So if there's 1 cord, it's a counter. It's counting how many cars pass by. If there's 2 cords with a little bit of distance in between them, then it's a speed tracker, and it's tracking how fast the cars that are driving by are passing. The city will check things like speed or number of cars for traffic flow to determine whether a street needs to be widened. Okay? So if you have an issue on your street, if you think that the people that are driving down your street are driving way too fast, you're part of the neighborhood watch, and you go to the city council or the county board of supervisors and ask them to put a speed bump in, well, speed bumps cost thousands of dollars to build. You wouldn't think it does, but when you throw in the materials cost, the labor, and the city planning, it all adds up to thousands of dollars. So they're not going to spend thousands of dollars on a speed bump if there's no good reason to. So what they'll do is they'll give you a box, and you put the box out there, and it'll be one with the two cords because the two cords measure speed, and then you'll collect data over a period of time. And then you'll bring it back to them, and they will compile the data and determine what the speed of the cars flowing down the street are. And if that speed is far above the speed limit for the road, then they will make an adjustment and say, hey, you do need a speed bump, and then they'll approve that project. So it's not an outlandish thing. It's the kind of thing that actually occurs on a day-to-day basis in the city. How do you justify some kind of a public work like a speed bump? And it's all about statistics and data. So let's take a look at our solution. We know that the sample is random and sigma is known with n equal to 100. So our H naught is that the average is less than or equal to 35, because we're going to accept the speed limit as being true and see if our evidence shows that it's actually false. So if H naught is mu less than or equal to 35, then HA would be mu greater than 35. And of course our alpha was 0.05. That's actually usually where the government sets their level of significance, is 0.05, the 5% level of significance. Now we know what test type we have. Because the HA has a greater than symbol, this is going to be a right-tailed test. So how does the right-tailed test work? Well, we need to find our z-score. So z equals x bar minus mu of x bar over sigma of x bar. The x bar is the average that we found from our calculations on the data that we got, and that would be 36. So we saw for the cars that passed by, there was an average speed of 36 miles per hour, minus the mu of x bar, which we set at 35, and then over sigma of x bar, which is sigma divided by the square root of n. Sigma was 4, square root of n was 100 cars. So then this is 1 over 0.4, which is 2.50. Once we know the z-score value, we can turn to the standard normal distribution table. So let's do that. We need the positive side of the standard normal distribution table, and we're looking for the z-score equal to 2.50. So when we find the z-score of 2.50, what's the table value? Well, it's 0.9938. So let's go back, get rid of that stuff, slide this up to give ourselves a little bit more room. So we just said that when z is 2.5, that the area to the left is 0.9938. But remember, this is a right-tailed test. We don't want the area to the left, we want the area to the right. So to do that, we subtract the 0.9938 from 1, which gives us a p-value of 0.0062, right? The area from the standard normal table is area to the left. In the right-tailed test, we want area to the right, so we have to do 1 minus 0.9938. That's where the 0.0062 comes from. So now we have our p-value. Once we know the p-value, we can do the p-value comparison test. If p equals 0.0062 and the alpha is 0.0500, then we can see that p is less than alpha. If p is less than alpha, then that means we reject H naught. What was H naught? H naught was that the mean was less than or equal to 35. So let's interpret those results. That means we have enough evidence to reject H naught But rejecting H naught means we're supporting HA. And HA was the claim that we were making as part of the neighborhood watch that the cars are going too fast. So we've got enough evidence to support the claim that the mean speed is over 35 miles per hour. So now we've presented this to the county board of supervisors or the city council, and we said, here's our evidence. We have enough evidence to support the claim that the speed is faster than the speed limit. So can we please have our speed bump? And they will generally approve those requests. Now, it might not happen automatically or immediately because of budgetary issues, but it'll be on the list of projects to be performed over the coming years. Okay, so here's a practice problem for you. One of your distributors reports an average of 150 sales per day. You suspect this claim is inaccurate. You randomly select 36 days and determine the number of sales each day. The sample mean is 144 sales, and the population standard deviation is known to be sigma equals 15 sales. At the 0.02 level of significance, is there enough evidence to doubt the distributor's claim? So try to work through that example the way that we just did our example. Pause the video, and when you're ready to see how it works, press play. Okay, so let's go ahead and look at this practice problem. First things first, does it fit the description? The sample's random, we do know sigma, and n is 36. So let's state our hypothesis. The null hypothesis is mu equals 150. That was the claim being made by the distributor, that his sales were 150 per day. Now for the alternate hypothesis, if the null hypothesis has an equal sign, the alternative hypothesis has a not equal to sign, so our HA is mu not equal to 150. Because that has a not equal to sign, we know we're looking at a two-tailed test here. Alpha is 0.05. And so we've got our z-score. We need to find that value. Z equals x bar minus mu of x bar over sigma of x bar. The x bar that we found was 144. So we have 144 minus 150 over 15 divided by the square root of 36. 15 was our standard deviation. 36 was our sample size. Plug this into your handy-dandy calculator. You get negative 6 over 2.5. which is negative 2.40. So once we have our z-score, we're going to go ahead and look that value up on the standard normal distribution table. Let's look at a sketch. Remember, we're doing a two-tailed test, so we need the p-value to be the combined area between those two tails. So we're going to find the area in the left tail, double it, and that'll give us our p-value. So let's look at that distribution. We need the negative side to get that negative 2.4. So if our z-score is negative 2.40, then the table value is going to be 0.0064. 0.0064. So let's go ahead and go back and insert that into our process. This is where we were at. And so now, if z is negative 2.4, then the table value gives us a 0.0082, but we're doing a two-tailed test, so we need to double this. So the p-value is 0.0164. Now we're going to take the p-value and compare it to alpha. P is 0.0164, alpha is 0.0200, so p is less than alpha. And if p is less than alpha, then our decision is to reject H naught. H naught was the claim that was made by our distributor. So that means there is sufficient evidence to disbelieve the distributor. If we're going to disbelieve the distributor, then this may result in our distributor being demoted or fired if we feel like they're lying to us. These are the kinds of statistical investigations that can change people's circumstances, that can have people lose their jobs. Or if we see that they're telling the truth, then it's the kind of thing that can get a promotion. So these are real world consequences that can happen because of statistics. So there's another way that we can make these decisions besides using the p-value decision rule. And that other way is by using something called rejection regions. So the way that rejection regions work is that you're going to start with your alpha and whatever your required test is. Is it a one-tailed test, a left-tailed, a right-tailed, or is it a two-tailed test? Then you're going to find a z-value from the standard normal table so that the area of alpha is contained in the tail. So instead of finding the p-value in the tail, we're going to find a tail or two tails whose area is alpha. And we're going to call that value z0. So for a left-tailed test, this is what it would look like. Our z0 would have our left tail, and then the area in that tail would be alpha. For a right-tailed test, it would be similar, but only we're in the right tail now. We have our z0 value, and alpha is that area. And then for our two-tailed test, each one of those areas is not going to be alpha. It's going to be half of alpha, because remember that when we're doing a two-tailed test, we're combining the area in the two tails. So if you take alpha over 2 plus alpha over 2, that's our total of alpha. So you'd find z-scores that would make each tail be alpha over 2. So once you've got our rejection regions, that's the shaded area. The shaded area is the rejection region. You're going to find the z-score for your data, and then look at where it falls on the distribution. If it falls in the shaded region, then you're going to reject H0. If it falls outside of the shaded region, you're going to fail to reject H0. So let's see how one of those is going to work. A coffee shop claims that its fresh brewed drinks have a mean caffeine content of 80 milligrams per 5-ounce serving. You are asked to test this claim. You find that a random sample of 42 5-ounce servings has a mean caffeine content of 83 milligrams. Assume that the population standard deviation is 35 milligrams. At alpha equals 0.05 level of significance, do you have enough evidence to reject the shop's claim? And we want to use rejection regions to solve this. We could do the p-value decision rule process as well, but we just want to try out this new process to see how it works. All right, so the sample is random, sigma is known, and n is 42. Mu equals 80. That is the claim that is being made by the coffee shop. They said that the mean caffeine content of their drinks was 80 milligrams. Mean is 80. So that is an equality statement. That's our H0. So its complementary pair for the alternative hypothesis would be HA not equal to 80. And then our alpha value was 0.05. Now because the HA has a not equal to sign, this is a two-tailed test. We need half of the alpha value to be in each tail. And the alpha value is 0.05, so we're looking for 0.025 in each tail. That means we've got 0.9500 in the middle, right? Because remember, the area under the total curve is 1. So 0.025 and 0.025 in the tails is 0.05, which would leave 0.9500 in the middle. So what z-score values correspond to that? Well, let's slide this up and give ourselves a little more room to work. So this is actually the same process that we used when we were finding confidence intervals. The centralized area, remember, would be our level of confidence. And then we would find a z-score that made that happen. I gave you a little table of frequently occurring values, and 0.95 for our c value was on that table. And that led us to z-scores of plus or minus 1.96. So those are going to be our z0 values, negative 1.96 and positive 1.96. So now we're going to find our z-score from the information. So z equals x bar minus mu of x bar over sigma of x bar. The x bar is the average we found. We found the average of 83. Mu of x bar is their claim, which is 80. 35 was the standard deviation, and the 42 was our sample size. So when we input that into our calculator, we end up with 0.5554. So where does that fall? Well, that doesn't fall in either tail, right? Because this would be negative 1.96, and these would all be negative 1.9798, all the way negative 2, negative 3 to the left. And then on the right, this would be positive 1.96, and the area to the right would all be 1.97, 1.98, 2, 3, larger values. 0.5554 would be in the central region, not in one of the shaded tails. The shaded tails are the rejection regions. That's where we would reject H naught. But if Z falls somewhere outside of that, then our decision is going to be to fail to reject H naught. So that's our answer here. We fail to reject H naught because it fell outside the region that was shaded. So it's just an alternative way to do it. Whether you use the p-value decision rule or rejection regions, you end up with the same decision, either rejecting H naught or failing to reject H naught for any given problem. So that brings us to an end of section 7.2. Look for your homework on Pearson, and have a great day.